All right, thank you. Yeah, so I am so excited to be here. I'm so excited to be virtually back at ICME. And the thing I'm most excited to talk to you guys about today is all of the different projects that I've gotten to work on and problems I've gotten to solve in solving real computational math problems in industry. So that's what I'm going to focus on, and I'm going to go through a number of different examples of actual real world problems that I've gotten to solve, and kind of through that, I'll walk through the different few steps of my career. So you'll pick that up along the way. But yeah, just excited to talk to you guys about using things that you actually learn in ICME in the real world. So let's see. All right, so first, of course, obviously it all started at ICME. This is a picture of me and Michael Saunders, who I was lucky enough to get to work with on a couple of projects. I think that's a picture of us at Informs in Austin one year, and I got to go on another trip with him to Iceland, which was really cool. So we had some good times. The other picture is me and my sister, who was pregnant at the time with her daughter, who was now almost 9, which tells you when I graduated. But that's crazy. But yeah, so my time at ICME was amazing. It was so much fun. The people, they're incredible. The community, most of my close friends are still my friends from ICME. I talk to them very often and still hang out with them all the time. So ICME was definitely home, and I am so grateful for the people I've met there and the community. And I'm especially grateful for all of the amazing things I got to learn when I was there that I still use every single day now. The good stuff, I graduated in 2012. My advisor was the amazing Professor Yin Ye, who was such a great advisor to me, and I'm sure is still an amazing advisor for everyone. I'm so grateful I got to work with him. And we got to work on some super cool projects. My thesis was made up of 2 main projects. The first one was on STPs for sensor networks. So Professor Ye has done a lot of work advancing STPs and solving them in polynomial time, which is amazing. And I got to contribute a small little piece to that, helping to figure out what conditions have to be true in sensor networks in order to solve things in polynomial time. So that was pretty cool. And we also got to work on a project with with electric vehicles. So 3 of my summers during grad school, I interned at a company called EPRI, Electric Power Research Institute. They're just down the road in Palo Alto. And it was great. They solved so many cool electricity problems. And I got to work with the electric vehicle group. And this was back in 2012. So electric vehicles were still new. And EPRI's office is right next to Tesla. So you felt like you were really in the heart of things. And the problem we solved was trying to figure out how to solve how to optimally charge a large fleet of electric vehicles. So if you have 100,000 electric vehicles on the road and they're all plugging in their cars at different times, you don't want to have too much impact on the electricity grid. So you kind of want to minimize that impact that you have. You don't want to be charging them all during peak electricity hours. And you also want to minimize the cost to the drivers. And especially now, these time of use rates for electricity are really common. So electricity costs different amounts at different times of day. So we wanted to minimize that cost to the drivers and the impact on the electricity grid. And you want to do it in real time as people are plugging in their cars. So we came up with this online optimization technique to dynamically decide whether cars should charge. And it was great fun, and it got me really excited about solving optimization problems in the real world and how we can actually apply it. So that was great. After I graduated, I wasn't quite sure what I wanted to do. I wasn't sure if I wanted to stay in academia or not. And I could have done a postdoc, and I decided instead to go to IBM Research, which I thought would keep my options open, and it did. I did research so that if I wanted to go back to academia, I could. I ended up not doing that, but it was great. It was a great time. At the time, IBM Research had just opened up this new research lab in Dublin, Ireland, and they were calling it the Smarter Cities Lab. So the idea was they would help design smarter cities, which is exactly what I was interested in. And they had an optimization group, which when I joined, I think was 4 people. And when I left, it was around 10 people. So it grew to a pretty decently sized optimization group of people doing cool optimization research. So it was great. I had a lot of fun there. I got to travel around Europe a lot, which was definitely the best part. About once a month, I went on a trip somewhere new. So that was really cool. the first project I worked on when I got there was with County Cork. So County Cork is a county in kind of the southeast region of Ireland. And they had this water system and they wanted to figure out how to optimally pump water. So the way it worked, this diagram here is a much simpler version. It was way more complicated than this, but they had this reservoir. And the picture I have here is actually a picture I took when I went to visit the reservoir. So that's actually the reservoir where they keep all their water. They have this huge reservoir of water and they have to pump the water from the reservoir into the treatment plants so they can treat the water and clean it. And then from there, it goes into these water tanks. And they had these two big water tanks where they stored all their water. And they were on a hill. And then the water flowed from those tanks on a hill down into the residential and commercial areas where people actually needed water. So what they wanted us to help with was, when should they be pumping water from the reservoir into the tanks to minimize their electricity costs, because they had these dynamic pricing where electricity prices were changing every 20 minutes or something. So they wanted to make sure they were doing this and spending the least amount of money on electricity. So it was a super interesting problem. It was especially difficult because we had to model the way water flows through a network, and the way water flows uses these equations that are not linear or quadratic or anything we know. It's like something to the power of 1.412 or something. So you have to approximate things, and there's so many different ways you can relax the problem. And on top of that, it's a really big network. So that meant there were a lot of binary variables, and it took us a really long time to figure out the best way to solve it. So we ended up going with a Lagrangian approach to kind of split the problem up and then put the solution back together. But that was really fun. That was a good project. And again, it got me interested in doing more applied projects. And I did a lot of other work at IBM when I was there. They weren't as, I didn't think they were as fun or interesting applications, but one that was super cool that I was so excited to get to be a part of. At the time, Cplex did not have an SDP solver, and they were trying to build an SDP solver. And so me and one other person, the two of us, got to do all this benchmarking to figure out how Cplex should build an SDP solver. So we got to test, should it be an interior point method? What kind of line search should you use? Should you use a predictor corrector scheme? We tried all these different things and tested every possible combination of things you could do to build an SDP solver. And then we got to go to Cplex and say, this is what you should do to make the fastest solver. So that was really cool. And I liked it a lot. And I had a great time at IBM, but after being there for 4 years, I'm a Bay Area native. So the weather in Ireland was kind of wearing on me. And I wanted a little bit of a change. And I was homesick. My parents are in San Jose. My whole family's here. So I ended up coming home almost 5 years ago now. And I joined a company called EndtoEnd Analytics, and it's a consulting company. So it was a little bit of a career change. I still do solve the same kinds of problems, but not in research anymore, in consulting. And consulting has been great. It was exactly what I was looking for. I've gotten to be on so many different projects. So every 3 to 6 months, we get to change what project we're on, which means you get to work with totally new people on a completely new application and learn about a whole new industry and just solve a whole new problem. So I've gotten to solve so many problems. I'm going to go through a few examples today of some of my favorites, but I've gotten to work on so many different problems. So I joined EndtoEnd 5 years ago. 2 months ago, we were officially acquired by Accenture. So now when I joined EndtoEnd, we were 40 people. In March, we were 80, and then we joined Accenture, which is a much, much larger company, but now we're still kind of like our own small subset within Accenture, where we're, solving the same types of problems, working with the same people on the same types of things. So EndtoEnd is a, analytics consulting company that started, I think, about 15 years ago, and it started as a supply chain, mostly focusing on supply chain problems. And these days, machine learning and AI and all of these analytics things are just everywhere. It's blown up. So now we solve all types of different problems, but most operations research problems are in supply chain. And because that's, the people we know are in that industry, we end up still doing a lot of those types of problems. And I've been lucky enough to be on a whole range of different projects. I'm going to talk about my optimization projects, and I think I have one example of a prediction project that I got to be on too. All right, so my first fun example, this was a project we worked on a couple years ago. So one of EndtoEnd's clients is a very large bakery that I can't name, but it's the largest bakery in the US, which was confusing to me at first because I wasn't really sure how a bakery could be that big. But when you think of like Oro Wheat and Thomas's English Muffins and Boboli Pizza Dough, all of these things, there are companies that own all of those companies. So they just make tons of bread. And we've been working with this company for a while. And so they came to us a couple years ago to help them solve a network design problem. So they wanted us to help them figure out where their bakeries, which are kind of like factories, but where they should place their bakeries throughout the country and their distribution centers so that they're going to minimize costs. So they have stores, they distribute to all of these different stores all across the country. And all of those stores have demand for different kinds of bread. And we need to be able to meet that demand at all the stores while deciding where those distribution centers should be and where the bakeries should be so we minimize the overall cost. And in our case for this problem, they had, I don't remember the exact numbers and I probably couldn't tell you anyway, but I think, they gave us 30 possible locations for 4 bakeries or something like this. So we had a finite number of options, and then within those options, we had to find the ones that were going to save them the most money. So this problem got complicated fast, but we ended up formulating this as a mixed integer linear program in Python and solved it using Gurobi. So actually at EndtoEnd, we are a premier partner of Gurobi, which doesn't mean that much, except that we work with Gurobi a lot. And when people want to use Gurobi and aren't optimization people, they come to us and we help them to formulate their problems and implement it and solve it for them. So we use the Gurobi for this problem. And our objective was to minimize the costs. And the costs got complicated. So one of the things I find a lot in consulting and solving problems in the real world is that a lot of the data just doesn't exist and it's not there. So if we wanted to minimize transportation costs, we had to actually figure out how much it costs to drive a truck from one state to another, and how much the fuel costs are in each state. And sometimes there are tolls on roads. You have to take the tolls into account. So there are all these costs that you have to figure out yourself. So we spent some late nights figuring out how to calculate these transportation costs. Labor costs are similar. How much does it cost to hire people in different states or different regions? There's a lot that goes into that. Production costs. It can cost a certain amount to produce something, and that can be different in different locations. And handling costs. So handling costs are like if someone brings a truckload of bread to a distribution center, someone has to unload that. They have to handle that bread and deal with it to bring it somewhere else. So there are all these costs associated. There are a lot of fixed costs for how much it actually costs to have a building in a certain location. So there were tons of costs that we had to take into account. So we had a huge cost function. Our decision variables were which products we made on which lines at which bakeries. So we have a demand at all of the stores, and we want to make sure we're meeting that demand. And we have to produce a certain amount at all of the bakeries to make sure we're meeting that demand. And we want to do that in a way that we minimize that cost. So we're making it a bakery that has a path to that store that's as cheap as possible. And the other decision variables were that path. So what should we make at the bakeries and how does it get to the stores? So there were a large number of binary variables that we had in there, what we were making where and how we're shipping it. And then given that, we had tons of production rules of things that we could and couldn't do. Obviously, there's only a certain amount of bread you can make in a given day on a certain production line, and every line might have a different speed. So you have to take that into account. And then there are certain things like if bread has nuts in it, that has to be separated from everything else. So you have these separations of things that can be made on certain at certain locations and bounds on how much you can make at each place. There were a lot of rules, like things like 75% of little bites have to go through a certain distribution center. So at this bakery, they have these things called little bites, which are like little donuts or little muffins, those little things you see in the store. And they're very specific about their little bites, and they always have been. And so those things have to be dealt with separately than everything else. And they have a lot of specific rules like that. And one thing I've found by working with real problems is that oftentimes the people that are implementing it and working with this every day, so much of the production rules are innate to them, and they don't always realize how explicit they need to make them. And these things are obvious. So there's so much back and forth between giving someone a solution and then saying, oh, I forgot to tell you guys that this isn't possible for X, Y, and Z reasons. There's so much back and forth of figuring out what actually works and adding more and more constraints to the model. Another thing, the last rule I have on here is that, and this one took us a while to figure out, and it's obvious now, but at the time we didn't quite realize it, but ideally, the amount that you're shipping in and out of a bakery and distribution center, you want it to be about a truckload. So all of this bread is being shipped on trucks. And if a truck can fit, say, 1,000 loaves of bread, and you have one route that has 1,200 loaves of bread, that means you're going to have a truck with 200 loaves of bread at 20% capacity, which isn't ideal. So even if it might minimize the cost, they're not really going to do that. So you kind of have to make it so that all of the routes are shipping bread that's in a truckload unit, not just in bread loaf units. So there's a lot that goes into it, and a lot of things that we kind of figured out as we were building it. But it worked. We built this solution and we went to them and we gave them the optimal network design of where they should put their bakeries and distribution centers, and they did it. So it was pretty cool. There were definitely challenges. The first one, like I said, solving a real world problem takes patience and time, and there's so much back and forth of figuring out what things were missing. And a lot of these problems I've worked on, you're basically trying to model the real world with linear equations. Your constraints, you want them all to be linear ideally. So you have this real world process, and you have to simulate the entire process in your constraints in your optimization problem. So it can get pretty big and it can get messy. And so keeping track of things and keeping straight what you've added and things like that is definitely a challenge. And solving things in reasonable time. This was a very large problem. We had so many different kinds of bread and so many strange constraints that, the first time we tried to solve it, it took forever. And that's, we didn't have time to have a problem that took 24 hours to solve, because we had to keep solving this and seeing if the solution worked and if it was good. So most of the effort went into making sure this could solve quickly so we could iterate on it as fast as possible. And when you have a problem that takes 24 hours to solve, if it's solved and it's not a good solution, or it breaks, or you lose internet connection, or whatever happens, it just, that's not feasible all the time. So solving things quickly is definitely key. All right, another project that I just finishing up, actually I had a meeting on this today, is a production scheduling problem. We worked with a glass company that is a startup glass company. They just started making glass in December of last year, so they're brand new. And I had not realized how interesting glass production was until I was on this project, but it's pretty cool. And it turns out most bottle types are all pretty much the same bottle type. So if you think of like a beer bottle or a wine bottle, they're all the same color, they're all the same size. Mayonnaise jars, salsa jars, there's just like a finite number of jar sizes that we have. And a lot of that is because it's difficult to start producing one bottle type and then change and produce another bottle type. So when you change that production, there's this whole process that you have of pulling the hot glass out of the furnace and putting onto the line, and you have to change all of the molds along the line. And that can take a lot of time. It can take a few days to change that over. And not only that, when you start producing a new bottle type, there's a lot of loss. So you end up producing bottles that are, not quite right. They don't pass the quality inspection at the end. And even as it is, you get like 80% of the bottles you make look good enough. That's the best they get. That's the optimal efficiency. So this changeover is really expensive. And this company, the startup company, wanted to disrupt the glass industry, and they wanted to produce kind of bespoke bottles for companies. They wanted to be able to produce a large number of different types of bottles, which is challenging. So they came to us and asked if we could help them create a production schedule that would minimize this changeover time. They wanted to maximize their efficiency and make as many good bottles as possible while making a lot of different types of bottles. So their plan is to make not just the standard, beer bottle, but a lot of different shapes and sizes and colors. So given all these constraints, for every pair of bottles, you have a certain amount of time it's going to take to change over. Similar bottles won't take as much time to change over if they're the same color, or if all you're changing is the neck size of the bottle, then it won't take as much time. So figuring out how you make all these bottles on this production line in a way that's going to maximize that efficiency. So again, we formulated this as a mixed integer linear program in Python. This one was different from the network design because with network design, we just had to give them a solution. We just had to say, we're going to run the program. We'll give you guys what you should do. And with this one, we need them to be able to run it. So that comes with a whole other set of challenges because they're not optimization people and they have, such an amazing skill set, but they can't always run code. So we have to build a whole tool around the optimization, and you have to make sure that no matter what happens, they will get a solution, right? Like the problem will never be infeasible, and you have kind of backups for everything that happens along the way to make sure that they will get a production schedule. And it won't not run. Of course, every code has bugs, so hopefully it will run every single time. But so far, we've been running smoothly. So this one was slightly different because we had to actually give them something. But it was still an optimization problem. Our objective was minimizing these changeover times, so figuring out how we can produce these bottles and maximize efficiency, and figuring out which bottles can be made on which lines on which days. And they had a lot of different production rules. You can make a couple different bottles on the same production line, but there are so many constraints to be able to do that. So that got pretty complicated. There are obviously limits on how much glass you can pull from the furnace to put into the production line. So you have those production rate limits. And there's also, you have they had three production lines. And so each line you could only pull so much, but the sum of those three lines could only pull so much from the big furnace that they have melting all of the glass. So that added extra constraints. And they had a lot of these strange production rules of things you could and couldn't make on lines. The last bullet point here, it was probably the trickiest thing that we had to figure out how to do. Every production line has a certain number of what they called sections, which is basically just like a mold that makes the glass. So they have a certain number of molds. And then you're pulling a certain amount of glass from the furnace into those molds. And how fast you're pulling that glass controls how many bottles you're making per minute. So if you're pulling it really fast and you have it on all of the same mold on, as the, 24 of those mold on the line, then you're going to make a certain number of bottles per minute. That's a lot because you're pulling a lot and you're running as much as possible. And we have to calculate how many bottles you're making per minute or per day because we need to know how long you're running it for. But you don't have to run it on all the sections. And sometimes you can't use all of your molds because the bottle's just too big and you can't pull enough glass. So it ends up getting complicated. And you have to multiply the number of molds times the rates that you're pulling the glass at. So we had these, multiplying this collinearity that made it a little bit tricky. And we had to try a few different things to see the best way to deal with it to make this problem solve quickly. Again, the user was running this, so we couldn't really have something that took 16 hours to run because, they might need something by that afternoon. So we had to try a few different ways to solve these problems and make it fast. So that one was very, very fun. One more optimization problem. We work with a big search engine company in the Bay Area. I've been on and off projects with them for the last 5 years. It's super cool. And this company has a lot of data centers all over the world. And these data centers are huge. Sometimes they're like miles long. So they have tons of machines in there. There's huge data centers with tons of servers and networking cables and all of this stuff. And all of these different components have different failure rates. So with those failure rates, you can figure out how many spare parts you have to keep of that for that part that might break in the data center. So one of my colleagues solved that problem and figured out how many spare parts we need of each part in each data center. And so I got to take that, and from that, we have all these data centers, and in this diagram, you can see they have these things they call hubs, which are like their big main data centers, and there aren't that many of those. And they have the smaller ones that are called spokes. And they keep all of their inventory at the hubs. And so if we know how many of these spare parts we have at each of the data centers, and we know the range that we want to be in, then we have to allocate all of the parts across all of these data centers to make sure that we have enough for those parts that might break. So this was a super interesting problem and had a few things that were tricky. For this one, the company already was using Cplex, so we ended up using Cplex for this, although just a few months ago, they have their own proprietary optimization solver, so they translated it over. But they were using my Cplex model for a few years, and they ran it every week on Tuesdays and Thursdays to figure out how to allocate all of the spare parts that they had in inventory to the different data centers so that each data center had the right amount that they needed. This was obviously a big mixed integer linear program. And again, this was something that non-optimization people were running. So we had to make it something that they could just press the button and get a solution and make it robust enough that they could actually use that. So the objective was to minimize our shipping costs. Again, shipping costs were not something we had, so we had to kind of estimate what those shipping costs were. And we also want to allocate the shortages across all of the data centers. So this is something that is pretty interesting. So a lot of these parts that they have in the data centers, sometimes there's a global shortage on them. So there just do not exist enough of the part in the world to satisfy the demand. So they just don't have enough. So it could be that, you know, at every location, you want 10 of a certain part, but there are only 5 that we have. So, you know, if we have this shortage, how do we decide which data centers get these parts, and how do we allocate them in a way that seems fair for whatever fair is, right? So you have to define what fair means and define what your metrics are. And then you have to allocate things accordingly. So that was definitely one of the challenges that we had to figure out. Our decision variables were which hubs should data centers receive these parts from. So given where we have the parts and where they are, how do we ship them out to data centers in a way that's going to minimize our overall cost? And of course, there were a lot of production rules. So we want to get as close as possible to this optimal range at as many data centers as we can, so they have the right number of parts. Another one of the challenges is that a lot of spare parts in inventory are replenished. So if something breaks and it's broken, you take it out, you replace it with a new one. But the one that you took out, you can replace, you can refurbish that, and you can turn it into something that does work. But it gets complicated because in a lot of supply chain applications, we have what we call a SKU, a stock keeping unit, which is the number that you associate with a certain part. So if you look on the back of anything you buy, there's a barcode that has some SKU on it that tells you what that is. But if you have a refurbished part, it will have a different SKU number. It's going to have a different ID number that you associate with it. So you have to match up those two, the refurbished parts with the new parts, and know that they're the same one and that you can use that as a spare part. So that was tricky. There are definitely some rules of some parts can go to different places, and there are a lot of rules of things that you can and can't ship. Like there are just countries that the US can't ship parts to. Or can't ship things of a certain cost to. So there are a lot of those rules that you have to add into the constraints. For this one, we created a lot of like Excel sheets. People in industry really like Excel. I was kind of anti-Excel beforehand because I always ran Linux, but now I have to use a Mac because Excel is very common and people really like it. So we end up having to do a lot of input parameters in Excel where people can go in and say things that can and can't happen. And then we read it in and turn that into constraints automatically. That's a big piece of what we do. This problem had a lot of challenges. One of them was this global part shortage. So one thing we found was happening is, let's say we only have 3 of a certain part. There are only 3 of them. And one location has 2 of them and one has 1 of them. And then we run the optimization, and for whatever reason, it decides to move one of the parts from location A to location B. So now it's a switch. So the one that, location A only has 1 and this one has 2. So and then it would shift the next week and it would transfer that one part back and forth. So we had to keep track of what we were doing before and all the moves that we had made to make sure that we're not repeating moves over and over again. So that was happening. Another thing we found was happening was the solution was giving us parts where it would move 10 of a part from location A to location B, and then that same part from location B to location C in the same quantity. So there were kind of these like triangular moves happening that even with our cost objective, it's still, because of certain constraints, was making these things happen. So we had to make sure that that didn't happen. And this was all things that we just caught over time. After a couple of months, people are in logistics are realizing they're making these shipments over and over again, and they have to come to us and say, this isn't working. So yeah, so this was cool. Again, we had to make this easy to use for the user. And this particular problem, they had to solve the same formulation on a few different data sets. So we had to set it up so it kind of all runs automatically and gives them all their output in one solution. So yeah, but it was pretty cool. This was pretty cool that they're still using this optimization solution, and that's how they figure out how to allocate all their parts. All right, and one last problem example. This one was not optimization. This one that I just finished this one up this year, a couple months ago. This was probably one of our biggest projects that we got to do. This one took a few years. And we built for the same large bakery. We were working with them for a few years on a number of different projects. And we built them this web-based user interface so that their planners, so people who plan how much bread they're going to sell at each of the stores, their planners can go into this user interface and see all of their past history of what they've sold at each store. And they also get a prediction of what they're going to sell in the future. And so my contribution was figuring out what the prediction is going to be. So given all of their historical sales, how do we provide estimates of how much they're going to sell of each product and each store for the next 12 months? So they had tons of data. And in order to build our prediction, this was all done in Python. We use scikit-learn. But the big part is really building the model. So getting all of the data and putting it into the right format so that we can build this data. So we take all of our sales history. We had like 3 years of sales history, and we took that, and that goes into the model, and the calendar. And the calendar is super important. And what that tells us is a lot of products have seasonality. So there are some products like hot dog buns that they sell way more of in the summer. So you have to keep track of whether it's January or July, because that will make a difference on how much you're selling. And you also have to keep track of holidays, because the 4th of July has a huge spike in hot dog buns. So you have to keep track of what week you're in, and then that will go into your prediction of how much you're going to sell over time. And pricing and promotions. So when something goes on sale and the price drops, that has a huge impact on how much you sell, right? When something goes on sale, the sales can be like 2 or 3 times as much as it normally is in a given week. So we want to keep track of that. One thing that I thought was really interesting when I got into this is that the bakeries they'll make all this bread, and then they give it to the stores, and they can tell the store, they can give the store a recommendation of how much to sell that bread for. But the store can decide what that price is. So the store gets to decide themselves what that price is going to be. And the bakery might not know what that price is, because the store has no obligation to come back to them and say, oh, we actually sold it for this price. So the bakery actually has to buy data from companies, either IRI or Nielsen, are these 2 companies that sell data on what those prices actually were in the store for every product. So the bakery has to go buy data to say how much their bread was actually sold for. So we have to take all of that price information into account to build this model of how demand fluctuates based on time of year, based on pricing and promotions and all of that. So we build this huge model, we pop it into our prediction engine, and we end up getting this prediction of our future bread sales that can change. And this was interesting because the planners who are using the tool, we want to give them a prediction for how much they're going to sell over the next year. But they also want to be able to see how that prediction will change if they change the price. So they want to say, if this item were on sale for this much in this week, then how does everything change? So the prediction has to be very dynamic, so that if you change any of the inputs, they can easily see how that will impact all of the output. I think I went over most of this already. We had 3 years of sale data. We had to add all these calendars and holidays. And for a bakery, there are some odd holidays that might have impacts, like National Donut Day, which does have an impact on how many donuts they're selling. So those are also holidays to a bakery. All the pricing information. We did all of this in Python. We use sklearn package, do all statistical methods, and used a number of different methods. And we actually used, it dynamically chooses which statistical method will give the best solution. And we actually created our own recursively squares method that updates in real time and takes in the last week of data. So dynamically it will update these predictions with the latest information. And all of this was integrated into this larger platform, this whole big web UI that we had a lot of people doing a lot of work. That was the big chunk of the project, was building that. And it took a few years to build that out. And we just delivered this, I think 2 months ago, 2 months ago. So it was pretty cool. So now they're seeing these predictions in the tool. There were a few problem struggles. One of them is that there are a lot of combinations of products and stores and regions, and we can't check all of them. So I can build this and test it on 1,000 products, but there are 10,000 products. And so there's going to be one that it doesn't work for whatever reason, some edge case that I didn't see or I didn't think of, and my validation code didn't check for. So that was a bit of the struggle, is once we deployed this, there were some people who were seeing things that we didn't know were in there, and they had to come back and say, this isn't working. And you have to figure out why it's not working for this one case and fix it and make sure that you don't break anything else. So that was one of the challenges. There also was a lot of code. This was a very heavy coding project, and the more code you have, the more room there is for bugs. So I hope that we found most of them or all of them, but there's definitely more room for error when that happens. All right. As you could probably tell, I'm very excited about solving optimization and prediction problems in the real world. I've gotten to work on so many. I only told you guys about a few, but I feel very lucky that I still get to use computational math in the real world every day and solve these real world problems that I feel like have an impact and are actually seeing a solution implemented in the real world. So that's great. One of the main challenges is definitely simulating the real world with a formulation. It's, the real world is full of humans and people making mistakes and things going wrong and things not fitting into linear equations. So trying to simulate everything in a formulation is definitely a challenge, and making sure that you capture everything in that formulation is definitely one of the main challenges, especially the beginning of projects. Most people using the tools we build are not used to running code. So as consultants, we build these tools for people who are in the weeds of the business and have amazing skill sets, but maybe have never seen code. And so we have to build these tools that are easily accessible for them. And then give them something that they can run on their computer. So that is definitely part of the challenge. And there's a lot of technical challenges that I didn't expect of figuring out sometimes. Like, I don't know why this isn't running on your computer, but it runs on mine. It's still on me to figure out how to get that working for them. And occasionally there's a trade-off between optimality and how long it takes to solve something. I think I definitely learned that over time, and I have to remind myself often to step back and see the bigger picture. A lot of times you might take 16 hours to find an optimal solution that says something will cost $10. And that takes 16 hours to get there. But in 2 minutes, you can find a solution that'll cost $10.10. And nobody really cares about the 10 cents. And so you just have to remind yourself that like the optimal solution, to how much does it matter? And how important is it? And can we kind of relax this to make it a lot simpler to solve and get something that's still pretty good? So there's definitely a balance in there that I think I have to remind myself of often. And in theory, the optimal solution is the best thing, but in practice, it's often hard to actually get there. So there are definitely challenges, but obviously, solving actual problems for real people and seeing the solutions implemented is very fun and very rewarding. That being said, Accenture is a great company. And if you are as excited about solving real problems as me, Accenture is a great place. It's a really big company. It's over 500,000 people, which is very large. And I was coming from a small company. So it can be intimidating, but we are definitely a small group within a really large company, especially end to end. We still kept our name and our emails and everything. So we're still a group of 80 people that are analytics people. And half of us are PhDs, the other half are all masters with analytics backgrounds. And we're analytics people, this small group of us inside a larger company. But the great thing about it being part of Accenture is they have so many resources. So when you're part of a big company, you have access to a lot more that we didn't have access to before. And there are a lot more people who have worked on all types of projects. So we already have benefited from being able to talk to people who have solved similar problems or seen other things in industry that are helpful for us. And so we are actually part of a group that's called Applied Intelligence. It's AI, but it's not the normal AI that we're used to. It's called Applied Intelligence, which is, again, a small group within the larger Accenture of a lot of analytics people. And there's a large focus on doing really cool work. So already I've seen that it's a great community and they really do care about doing cool analytics. And there's a lot of investment into the research and things like that. So Accenture is a great place. And if you're interested, you can always email me. We are always hiring. As of now, I'm the only ICME person, but we have many MS&E people. I am the only ICME person so far, but I would love to have more ICMEers join us. We do lots of cool things and solve really cool problems. And it's a great place with great people.
Fantastic. Well, thank you so much, Nicole. That was wonderful hearing how you're applying all these areas of computational math and optimization to so many different problems in the real world. And we have a ton of questions here.
Okay.
I'll start with one because I was interested in this too. I think it came up when you were talking about the glass production, the changeover, but really applies to all of them. And this is from Matt Johnson about where do you even start with something this complicated? And I guess my part of the question would be the role of an interdisciplinary team. You're not the domain expert. You have to pull in these domain experts. How do you do that? And Matt's asking, do you start writing out equations and just try to fit them together? So if you wouldn't mind, from both the interpersonal standpoint, the people part, as well as the technical part, where do you get started?
Yeah, that's a good question. I think for that one, you can see I drew out this diagram. I spent like 3 hours drawing out this diagram. And a lot of it was, we went to the client and they described the problem, but we have to make sure that we understand it. So the first thing that we do is we draw it out and we show it to them and say, is this what it looks like? And they'll tell you, no, there are these other things in here. And they have to explain every piece of it, but we draw it out and show them diagrams of how we see it working. And then we usually we'll write out all the constraints in English sentences and say, does this make sense? Do you see anything missing? We usually don't show them any equations. So it's really just understanding at a high level, does all of this make sense? And then once we can show them a solution and we can say, here's the schedule, which in itself is hard, right? Because you don't want zeros and ones. You have to turn it into something that is understandable to them and easy to read and they can glance at and know what it is. So yeah, once you can give them a solution, that's really when a lot of it starts, because then they can see the things in the solution that don't fit the way things actually work. But yeah,
Nice.
that mapping out at the beginning. And I've, internally as consultants, right now, all of us are analytics people. So all of the business insights we get are from the client and what they know.
No, that makes sense. And then once you get all that rich information, do you as the internal team then start by writing equations, or how do you frame that conversation internally once you get all that rich input from the client?
Yeah. Then we start writing code and writing it up as equations and start building something out, start building the formulation out.
I see.
Yeah.
Okay, great. Here's one that kicked off the questions is CPLEX SCP solver. The question is, seems not to have been materialized or as a commercially available IBM product. Anything you want to comment about that? I saw you mentioned that.
I know. I actually didn't know that. I probably should have known that, but I didn't know that. I nowadays I almost always use Garobi, so I'm not sure. I don't know what happened with that. Yeah.
Okay.
I have to check.
Okay. Here's a question about the bakeries and how many bakery constraints were not real constraints, but just a bakery company employees' rule of thumb as to what would be a good thing to do, but perhaps winds up being suboptimal in a proper optimization problem.
Yeah, that's a great point. That's very frequent. Yeah, where that happens, where, I think we had one that, they had 75% of this product should go through here. And it seems pretty vague, and there were quite a few things that made it suboptimal. And we actually came up with solutions that met all their rules. And they said, no, we can't do that because we don't like the idea of having, a place here or a place there. And there were some that seemed more reasonable. I think like there were some locations where they just didn't want to, they would have to lay off everyone that worked at that place, and they didn't want to do that for various business reasons. So even though it would be more expensive, it was going to be bureaucratically like bad. So there were just some things that seemed reasonable, but there were definitely some rules of thumb that were like, I don't know. I mean, that definitely makes the objective worse, but they have their ways of doing things.
Here's a question. In general, in what form did you deliver your software to your customers that are not software experts? In the form of Jupyter notebooks, Python scripts, or something else?
Yeah, it definitely varies based on the client. So I think of the examples I gave here, the things we delivered were in Excel. So you can write VBA code behind Excel that will just call Python scripts and call your code, and then you can write things back to Excel. So that's a common one for a lot of clients who aren't super familiar with code. But there was a project I did a couple of years ago with the company that had a whole data science group. And so we did some machine learning for them, and then we could give them the Python code, and their data science team took that on. And we built an API for them so that would take the solution and put it back into their website where they could use it. And it would pop out to their customers and things like that. So we built them an API, but we gave them the actual Python code, and then their data science team just took it and maintains it and all that. And so that's ideal because then we don't have to do a lot of the user interface stuff. And building user interface can be fun, but it takes extra time. And we have a lot of projects, so sometimes there's not always time to do that extra step. So when you can just give someone the code and have them run it, it's a lot easier.
Here's a question from Professor Yi. When using optimization tools, do business people care about sensitivity analyses and dual information?
Oh, that's a great question. I don't think I've had anyone who knows enough to know that that's important. So yeah, I think we had one project where we did look into the dual solution because we were using prices. And so we kind of had to explain to them what shadow prices were, and we used it, and it was part of what we did. But for the most part, we haven't had anyone care about sensitivity analysis yet. Yeah.
Interesting. you will see that more and more over time, I imagine.
Yeah.
Here's a question regarding the data centers problem. Could you speak more about the tools and concepts used? To what extent did the data provided by the client influence your approach?
Yeah, so for that one, let's see, we had to build something where they had all of their data in a Sheets application, which probably gives away who they are, but they had all their information in Sheets. And so we had to read a lot of it in from there. And they had some data in a database that we could also read in. And it definitely influenced the way we solved the problem. And, you know, the way things work in companies is so much worse than I thought it would work. Like things are always held together with duct tape. And you're like, how is this working? I don't know how you're staying afloat. But yeah, it wasn't as clean as you would expect. And sometimes they had a bunch of different data sets that they wanted to do things totally separately. And so we definitely formulated the problem in a way that gave them the solution and the weird way they wanted it, because their data was separated in different ways. So that had an impact on it. And they had CPLEX already, and they wanted to use the CPLEX programming OPL, optimization programming language. So we, had to do things that way. And we had to build it though that, so we wanted the user to press one button and have it run all the way through. So I think I had to do things in like JavaScript or something so that it could call all these optimization problems just from one button press. So there were some things like that made it extra complicated because the data was in a strange format.
Let's see, I have one more question here. Let's see. This is on the last one on the prediction problem. Were there aspects of the bakery sales prediction problem that were especially optimization heavy?
I don't think so, no. I think it was mostly all statistics for that one. Yeah, I can't think of much optimization that we did there.
Okay. And here's one last one that just came on. How important are stochastic and stochastic robustness considerations in the optimization problems you've solved? Does everyone just plug in expected values and treat the problem as deterministic?
Yes, that's a great point. I think we should use robust optimization more than we do, but yes, for the most part, I've done a few projects where we have used robust optimization and made sure that it will work, even with sensitivity and things like that. But for the most part, we have just used expected values and assume that will be good enough for the client. Yeah.
Well, I think that's about all of the questions on here, and we're just at the hour, so that's perfect. Thank you again. It was an excellent talk, and definitely any students who are interested in reaching out, sounds like there's some really great opportunities at Accenture. So hope that works out.
Yeah, great. Thank you. This was awesome. Thank you for having me.
Yeah.
Our pleasure. Bye, everyone.
Okay.
Right. Great talk,
Bye.
Nicole.
Thanks.
We should get in touch. Okay.
Okay.
Once pandemic is over. Okay.
Okay. All
Take
right.
care. Okay.
You too.
Yeah.
Bye.
Bye. Bye. Great talk.
Thanks.